Hi, everyone. This is the last permutation on the particle in the box problem that I want to talk about, called a particle in a two-dimensional box, described in Atkins 7D3. And as the name suggests, this is a lot like particle in a 1D box, except now it can move in two dimensions. It can move in X and it can move in Y. So here's a sketch of what that would look like, right? Here's my particle. It's moving in X and Y, and I'm going to write in blue. So classically, this would just bing back and forth. I imagine some length of the box in the X dimension. I'll call that Lx. There's some length of the box in the Y dimension. I'll call that L sub Y. Inside of the box, the potential is 0. And outside the box, the potential is infinite. So everything is analogous to the 1D particle in the box, except for the fact that this can move in two dimensions. We're going to write it. We're going to solve this problem just like we did before, which is to start by writing the Schrodinger equation. So here goes. H psi equals E psi. H is the Hamiltonian operator. I'm going to get a kinetic energy term. And this is for motion in the X dimension. So this is, this is kinetic energy in the X dimension. I'm going to get another term for kinetic energy in the Y dimension. My pen just went away, but it's okay. So this one is for kinetic energy in the Y. In theory, there could be a potential term. We're inside the box, so this is 0. And this is going to be equal to E psi. Now, this looks very similar to the particle in a box, except for one important difference, which is that this differential equation depends on two variables. It's a multivariable problem. And so we need some new techniques to solve it. And the technique that we're going to use, we'll see throughout the semester, it's called separation of variables. So here's the idea. The goal is to start with one equation, which is a function of two variables. And we're going to turn it into two equations, which are each a function of one variable. So we're going to separate these two variables. And I'll walk you through this. The first step when you use a separation of variables technique is to guess a solution. And specifically, you're going to guess that the solution function, in our case, the wave function, can be written as a product of two one-variable functions. In other words, our wave function, which depends on X and Y, can be written as a product of one function which only depends on X and one function which only depends on Y. So I'm going to call the function which only depends on X, capital X, and the one which only depends on Y, capital Y. Once you make that guess, you insert this into your differential equation and start simplifying. Here goes. Negative h bar squared to m xy dx squared plus negative h bar squared to m d squared xy dy squared equals e xy. This is a derivative with respect to x. X only depends on x and y only depends on y, so it is in effect constant, and I can pull it out. Same thing over here, except now it's the function x, which does not depend on y, so I can pull it out. And I've started to simplify. At this point, we're ready to move on to step 3, which is to collect variable terms on one side of the equation and constant terms on the other. I will go back and show you this, but these are all variable terms. Capital X's are functions, capital Y's are functions. I got functions over here. I want all of my variable terms over here and my constant terms on the right-hand side. And so the way functionally that I'm going to do this is to divide through by capital X, capital Y. And if I do that, here's what I end up with. At this point, you've done something very important. And we put all the variable terms on the left-hand side, right? Constants on the other. And we ask sort of a thought experiment question. Right? Note that this only depends on X. This only depends on Y. And energy is a constant. It's the eigenvalue. What would happen if I varied X? Right? Could these functions change? Right? Well, this is a function which depends on X. So if I varied X, this function could change. If I varied X, this function only depends on Y. And since I'm only changing X, this can't change. It's constant. If I change X, my constant has to stay a constant. So look at this. Something which could change plus a constant is equal to a constant. What does that mean? It means that this function must be a constant. That's the only way this works. And so at this point, what we say we've done is we've separated the equation. That is, I can write this equation as follows. Negative h bar squared 2m 1 over x d squared x, and I should write this dx squared equals ex. I'm going to get a second equation, which looks like this. It's E. Look at these expressions. If I look at these separated equations, right, these are only functions of one variable. This statement is entirely consistent with the previous one. Right? I've taken this function, which depends on x. I reasoned that it had to be equal to a constant, which I could call whatever I want. Here I called it ex. Same thing is true with y. I called it ey. And if I put the condition that ex plus ey equals e, this is entirely consistent with my previous statement. right? It's separated. And this is important because I can rearrange this equation. T squared x, x squared, x. If I bring my capital X over here, right, what does this look like? Right? Well, I have different variables. I have x's and ex's, but I hope you recognize that this is just the one-dimensional particle in the box. And therefore, the solutions are exactly the same. X equals 2 over Lx to the 1/2 sine n x pi x on Lx. Ex equals nx squared h squared over 8mLx squared. I can write those because I know the 1D solutions. Now let me point out that I have to put subscripts x on my length. I also put them on the quantum number n. Right? This is only associated with the x dimension. I'm going to get a similar set of equations for y. And at the end of the day, here is the solution. Right? When we solve the Schrodinger equation, we get wave functions and energies. Here are my wave functions. A 1D particle in a box in x. You can't see this. A 1D particle in the box for y. And the two-dimensional wave function is the product of these two. I get a one-dimensional energy in x. I get a one-dimensional particle in the box energy in y. And the total energy is the sum of these two. We have solved the Schrodinger equation. The last step in our process is to interpret this, tell us what this means. And I will do that in the next video. All right, I'll see you then.